Isothermal microcalorimetry (IMC) is a laboratory method for real-time monitoring and dynamic analysis of chemical, physical and biological processes. Over a period of hours or days, IMC determines the onset, rate, extent and energetics of such processes for specimens in small ampoules, for example 320 milliliters, at a constant set temperature, circa 15 degrees Celsius 150 degrees Celsius. IMC accomplishes this dynamic analysis by measuring and recording versus elapsed time the net rate of heat flow microsine J seconds equals microsine W to or from the specimen ampoule, and the cumulative amount of heat J consumed or produced. IMC is a powerful and versatile analytical tool for four closely related reasons. 1. All chemical and physical processes are either exothermic or endothermic, produce or consume heat. 2. The rate of heat flow is proportional to the rate of the process taking place. 3. IMC is sensitive enough to detect and follow either slow processes, reactions proceeding at a few percent per year in a few grams of material, or processes which generate minuscule amounts of heat, for example metabolism of a few thousand living cells. 4. IMC instruments generally have a huge dynamic range, heat flows as low as ca. 1 microsine W and as high as ca. 50,000 microsine W can be measured by the same instrument. The IMC method of studying rates of processes is thus broadly applicable, provides real-time continuous data, and is sensitive. The measurement is simple to make, takes place unattended, and is non-interfering. For example, no fluorescent or radioactive markers are needed. However, there are two main caveats that must be heeded in use of IMC. 1. Misdata. If externally prepared specimen ampoules are used, it takes ca. 40 minutes to slowly introduce an ampoule into the instrument without significant disturbance of the set temperature in the measurement module. Thus any processes taking place during this time are not monitored. 2. Extraneous data. IMC records the aggregate net heat flow produced or consumed by all processes taking place within an ampoule. Therefore, in order to be sure what process or processes are producing the measured heat flow, great care must be taken in both experimental design and in the initial use of related chemical, physical and biologic assays. In general, possible applications of IMC are only limited by the imagination of the person who chooses to employ it as an analytical tool and the physical constraints of the method. Besides the two general limitations, main caveats, described above, these constraints include specimen and ampoule size, and the temperatures at which measurements can be made. IMC is generally best suited to evaluating processes which take place over hours or days. IMC has been used in an extremely wide range of applications, and many examples are discussed in this article, supported by references to published literature. Applications discussed range from measurement of slow oxidative degradation of polymers and instability of hazardous industrial chemicals to detection of bacteria in urine and evaluation of the effects of drugs on parasitic worms. The present emphasis in this article is applications of the latter type biology and medicine.